So now we'll talk about steady vortex flows, and these are flows that have circular streamlines. So down here I've sketched two circular streamlines. We'll consider r theta polar coordinates, and in that case the vector field is a function of r and theta, and as you can already see here, the streamlines are circular around a certain origin, so there is no radial component to your velocity field, and the velocity field is simply a function of theta, which does depend on how far from the origin you are potentially. So in the first case that we're considering here, number one, we'll consider solid body rotation. And for solid body rotation, our flow field theta is simply omega 0 r. And omega 0 is our angular velocity, and it's a constant. Yeah? So we have a constant angular velocity. So if we plotted a profile of we would say, okay, it's 0 at r equals 0, and then it increases linearly as you go out from the center of the vortex. So this line here is theta is omega r. Now let's consider one element, one fluid element, A, B, C, D, and we'll think about how that deforms and changes. And it has a center point P. So if your streamlines, say, are pointing counterclockwise, so your flow is counterclockwise around the origin, then after some time dt, your new element will be up here. So this is going to be A dash, B dash, C dash, D dash, and we have a point P dash in the middle. And so what you see is that every point A, B, C, D rotates around the origin at the same angular velocity omega 0. So the fluid element itself does not deform, it just rotates. Element rotates around P, around the center of the element, counterclockwise. Counterclockwise around P. Now, the vorticity of this flow is readily computed. Omega is the curl of u. And now you have to compute the curl of u in polar coordinates. And we can show that this is Ez, so the basis vector in the z direction. So again, the rotation axis is out of the page, and the vorticity is given by 1 over r, d by dr, r u theta, minus 1 over r, d by d theta, ur. And this is actually homework question 2 to show that that's the curl in polar coordinates. See homework question 2. So there are no theta or r components to the vorticity, which is not surprising. And also one more simplification. u theta does not depend on theta, it just depends on r. So this component also goes to 0. So we'll find that omega is really just Ez times 2 omega 0, i.e., or we can, in component form, you would write it as 0, 0, 2 omega 0. Let's remember from last time that the vorticity is simply twice the fluid rotation rate. And all the fluid elements rotate, therefore around P at rate omega 0. i.e., the fluid elements rotate around their center at the same rate as every particle rotates around the origin. At the same rate as every particle rotates around the origin. Now next let's consider the shear tensor, the strain rate tensor, and the strain rate tensor is given in polar coordinates by SRR, SR theta, SR theta, S theta theta. And if you look at U theta, just as a reminder from the previous page, it's omega 0 r, you will find that the strain rate tensor is 0. All the components are 0. So there is no deformation. And that's why this is a solid body rotation vortex. To show that this is really 0, you have to get the individual components here of SS, and they are dur dr, and up here it's a half r d by dr u theta over r plus a half 1 over r dur d theta, and that's the same as the other diagonal, of course. And then we also have down here we have 1 over r du theta d theta plus u r over r. Finally, let's consider the circulation of this flow around a streamline of radius r. So in that case, gamma, as we know, is the line integral of u dot ds, and for the streamline of radius r, we will have u at r is omega 0 r, and then ds will be r d theta, and we will go from 0 to 2 pi, so that is simply omega 0 r squared 2 pi. So The circulation, in this case, is simply 2 omega 0 times pi r squared, which is nothing else but the vorticity times the area of the loop that we consider here.